Every science fiction story you have ever watched told you the same comforting thing. If aliens exist, they will eventually find us. They will build better engines, they will master longer voyages, they will figure out the math, and one night the sky will fill with their ships. But here is what those stories left out. The math has already been figured out. Physicists have been doing it for over a century, and the answer is not the answer the stories needed. Alpha Centauri, the nearest star to our Sun, sits 25 trillion miles away. Our fastest probe, Voyager 1, has covered 0.06% of that distance in 48 years of nonstop flight. The energy required to accelerate even a small probe to 10% of light speed equals 7,000 Hiroshima bombs. The total amount of antimatter humanity has produced in 30 years of trying at every particle accelerator on Earth is 10 nanograms. Not 10 grams, 10 nanograms. The barrier is not engineering, the barrier is the universe itself. Get comfortable, hit subscribe if you are new here, because by the end of this, the night sky will never look the same to you again. Now, let's slowly ease into this. Part 1. The night sky lies. Look up at the night sky on a clear evening, somewhere far from city lights, and find two stars that appear almost touching, twin points pressed against the dark. Your eyes tell you they are neighbours. Your brain processes them as objects separated by a small gap, the way two street lamps look at the end of a long road. This is the most patient deception the universe has ever told. Those two stars might be separated by 50 light years. They might not even belong to the same spiral arm of the galaxy. One could be a red dwarf burning quietly 6 light years from Earth, and the other could be a blue supergiant blazing from 800 light years away, and the only thing they share is the direction your eyes happen to be pointed in tonight. The night sky flattens the universe into a dome. It collapses trillions upon trillions of miles of three-dimensional space into a flat painted canvas that your retina processes as a field of pinpoints. Every civilization that has ever looked upward has stood inside this same illusion. The illusion matters because it is the foundation of every casual assumption ever made about alien visitors. When someone imagines an advanced extraterrestrial civilization traveling to Earth, they imagine a journey. A difficult one, certainly. A long one, but fundamentally, a journey, the way a ship at sea undertakes a journey, with a port of origin and a port of arrival and a route drawn between them. The night sky encourages this kind of thinking. It makes the stars look like destinations on a map, like cities connected by highways. In reality, the space between stars is nothing like a highway. It is an ocean so vast that calling it an ocean is itself a deep understatement. The Pacific Ocean, at its widest stretches, 11,000 miles. The distance from our Sun to the next nearest star, Alpha Centauri, is 25 trillion miles. The Pacific Ocean fits inside that interstellar gap more than 2 billion times. Hold that number in your mind for a moment. 2 billion Pacific Oceans laid end to end, and you still have not reached the closest star to the one you are sitting under right now. This illusion persists because human perception evolved for an entirely different purpose. Our ancestors needed to judge the distance to a predator, the reach of a thrown spear, the width of a river. The human visual system is calibrated for distances measured in feet and yards and miles, perhaps hundreds of miles, from a mountaintop on a clear day. Nothing in our evolutionary history prepared us to intuitively grasp distances measured in trillions of miles. When we look at the night sky, our brains do what they have always done. They simplify, they flatten, they turn the incomprehensible into a manageable picture. And this single cognitive shortcut has quietly distorted every popular conversation about whether aliens could ever visit Earth. There is a thesis at the center of this video, and it is worth stating now so the rest of what follows can be measured against it. The barrier is not technology. The barrier is reality. The reason no civilization, no matter how advanced, can ever physically reach Earth from another star is not that they have not yet invented the right engine. It is that the universe itself is built in a way that makes such a journey effectively impossible. The night sky lies about distance. The next 2 hours are going to make that lie unforgettable. Once you understand what is actually behind those scattered points of light, you will look up at the same sky and see the same stars, and you will know what the universe has been hiding behind them. Picture, for a moment, a vast dark cathedral full of candle flames scattered across a floor too wide to see across. Each flame casts a small circle of light around itself. The dark between any two flames is total. We will come back to that cathedral by the end of this video, and the image will mean more then than it does now. For the moment, just place it in the back of your mind. Settle in for a moment with that image, because we are going to return to it. A cathedral, dark and vast, with small flames scattered across a floor too wide to see. It is a metaphor that science fiction has used before, and the version offered here owes a debt to that lineage. But the cathedral is going to mean something specific by the end of the next 2 hours. It is going to mean the geometry of the place. It is going to mean the physical reason why, no matter how patient or clever or determined any civilization is, the journey from one flame to another is not a difficult journey. It is not a long journey. It is a journey the geometry of the room itself refuses. For now, hold the cathedral loosely in the back of your mind, and consider how the lie of the night sky has been told to every civilization that has ever existed on this planet. The Greeks looked at the same stars you are looking at and drew constellations across them. They imagined the points of light as part of a single dome, a celestial sphere with the Earth resting at its center. Their picture was wrong in nearly every important detail, but the picture was honest to what their eyes actually told them. The stars looked equidistant. The stars looked nearby. The stars looked like neighbors in a single shared room. 2,500 years of astronomy has given us better numbers, more careful measurements, parallax shifts and spectroscopic shifts, and gravitational lensing, and we now know how spectacularly wrong the picture is. But the eyes still tell us the old story every time we look up. The dome is still there. The pinpoints are still arranged into the same patterns. The illusion is more durable than the science that disproved it, because the illusion is built into the optics of the human eye and the architecture of the human visual cortex, and no amount of knowledge changes what the eye does. The sky still looks like a neighborhood. Part 2. The first wall is distance. Start with the closest possible starting point. Alpha Centauri sits 4.24 light-years from our Sun. That number sounds small. You could say it in under a second. But a light-year is not a human unit of measurement. It is an astronomical abstraction, a shorthand for a distance so large that no familiar unit can hold it without collapsing into nonsense. 1 light-year equals approximately 5.88 trillion miles, or 9.46 trillion kilometers, depending on which side of the metric system you live on. Multiply that by 4.24, and the gap to Alpha Centauri comes out to roughly 25 trillion miles, 40.2 trillion kilometers. The nearest stellar system, the galactic front door, the literal closest place outside the gravitational influence of our own Sun, 25 trillion. If you started counting to 25 trillion at the rate of 1 number per second, never pausing to eat or sleep or breathe, you would need nearly 800,000 years to finish counting. You would begin before anatomically modern humans had fully spread across the African continent. Every pharaoh would rise and fall before you reached the trillions. Every empire of bronze and iron would build its monuments and crumble back into the dust they came from. Every war that has ever been fought would be fought and forgotten, and you would still be counting. 25 trillion miles is the shortest possible interstellar trip from our solar system. This is not the average distance to a star. This is the closest one, and it is so far away that no human object has ever crossed more than a trivial fraction of the gap. Consider Voyager 1. Launched in 1977, it is the farthest human-made object from Earth. As of 2026, Voyager 1 is approximately 24 billion kilometers from us, which is about 167 astronomical units, or roughly 22.5 light hours. It is, this year, approaching the symbolic milestone of being one full light day from Earth. A command sent today would take nearly a full Earth day to arrive, and the reply would take another full day to come back. Voyager travels at approximately 17 kilometers per second. That is roughly 38,000 miles per hour. For comparison, a bullet from a high-powered rifle moves at about 1,700 miles per hour. Voyager is roughly 22 times faster than that bullet. It has been flying for 48 years, without stopping, without slowing, without deviating from its outward trajectory. In all that time, Voyager 1 has covered about 24 billion kilometers. That sounds impressive until you measure it against the interstellar scale. 24 billion kilometers is less than one single light day. Not one light year, one light day. Voyager has not yet quite crossed the distance that light covers in 24 hours. And one light day is 1/365th of a light year, and the nearest star is over 4 light years away. At its current speed, Voyager 1 would require approximately 73,000 years to cover the distance to Alpha Centauri. 73,000 years. Human civilization in its entirety, from the first agricultural settlements in Mesopotamia to the device you might be holding right now, spans roughly 12,000 years. Voyager would need 6 times the entire length of recorded human history to cross the distance to the next star. And when it arrived, it would not stop. Voyager carries no braking mechanism. It is not actually pointed at Alpha Centauri, in fact. Its real trajectory will eventually carry it past a star called Gliese 445 in about 40,000 years at a closest approach of 1.6 light years. After that, it will continue outward forever, a frozen relic tumbling through darkness with no destination and no purpose. It will join the interstellar medium as a piece of cosmic debris, slowly cooling toward the background temperature of space, carrying a golden record that no one will ever play. This is the reality of interstellar distance, not the sanitized version from science fiction, where ships jump between stars in minutes. Not the Hollywood version, where a single montage bridges the gap between launch and arrival. The real version, the version in which our fastest spacecraft would need 73 millennia to cross the smallest possible step between our sun and another. If an alien civilization launched a probe at comparable speeds toward Earth from Alpha Centauri, we would wait longer than human civilization has existed for it to arrive. And Alpha Centauri is the closest possible starting point. Now scale outward. Sirius, the brightest star in our night sky, sits 8.6 light-years away. That is roughly 50 trillion miles. Vega lies 25 light-years out, about 147 trillion miles. Betelgeuse, the red giant marking Orion's shoulder, sits approximately 700 light-years from Earth. Converting that number into miles produces a figure so long it would fill a line across your screen. These are all ordinary stars, in our own galaxy, in our local neighborhood. And the distances between them are already measured in ranges that make Voyager's 4-decade journey look like a single footstep on a continental hike. It is worth slowing down here for a moment, because the numbers can numb. 25 trillion, 588, quadrillion, 93 billion. Each one is a label that sounds like every other label after a while. Try a different approach. Take the gap from the Sun to Alpha Centauri and shrink it down to 1 meter, 1 ordinary meter, the length of a typical kitchen counter. At that scale, our entire solar system, from the Sun out past the orbit of Pluto, is roughly 1/10 of 1 millimeter wide, smaller than a grain of fine sand, almost invisible against the meter-long gap. And that gap between our solar system grain and the nearest other solar system grain is empty. Not almost empty, empty. A near-perfect vacuum with about 1 hydrogen atom per cubic centimeter on average, and roughly that density holding steady for the entire meter of the model. The grains of sand at each end of the meter are the rare interruptions in an overwhelming volume of nothing. Now extend the model. Sirius is about 2 meters from our grain at the same scale. Vega is about 6 meters. Betelgeuse is about 165 meters. The galactic disk, end to end, is roughly 24 kilometers wide at this model scale. 24 kilometers, with stars represented as grains of sand spaced 2 to 3 meters apart along the way. Walk it. 24 kilometers of mostly empty road, with the occasional grain of sand to remind you that this is, technically, a galaxy. That is not a metaphor. That is the scaled ratio. The Milky Way is, by overwhelming proportion, the volume between its stars, not the volume of the stars themselves. The stars are punctuation. The dark between them is the sentence. Part 3. The galaxy is mostly the gaps. The Milky Way galaxy itself spans approximately 100,000 light-years from edge to edge. That is roughly 588 quadrillion miles. Our solar system sits about 26,000 light-years from the galactic center, embedded in a minor spur of the Orion Arm, about 2/3 of the way out from the core. Light leaving one side of the galaxy would need 100,000 years to reach the other side. Not a spacecraft. Light. The absolute fastest thing in the universe. The cosmic speed limit that nothing with mass can ever reach. Even light, traveling at 670 million miles per hour, needs 100,000 years to cross our single galaxy. A human lifespan is roughly 80 years. Light crosses the Milky Way in a span of time equivalent to about 1,250 consecutive human lifetimes. Each one of those lifetimes would begin and end in total darkness between stars, surrounded by void, with a destination no closer to the naked eye than it was when the journey began. And the Milky Way is just one galaxy. The nearest large galaxy to ours, Andromeda, lies approximately 2.5 million light-years away. The observable universe contains an estimated 2 trillion galaxies scattered across roughly 93 billion light-years of space. These numbers exist so far beyond ordinary human intuition that they function as labels rather than descriptions. No human mind can genuinely picture 93 billion light-years. We can write the number down, we can do arithmetic with it, we cannot feel it. The universe is built at a scale that renders human experience, in the strict sense, irrelevant. Here is where this matters for the question of alien visitation. When people imagine extraterrestrial civilizations visiting Earth, they rarely think about where, in physical space, those civilizations would actually be located. The galaxy contains roughly 400 billion stars. Many of those stars host planetary systems. NASA's Kepler mission confirmed that planets are common across the galaxy, with most stars hosting at least one world and many hosting several. Some percentage of those systems will contain a planet in the habitable zone, the orbital distance at which liquid water can exist on a rocky surface. A 2020 study by Kunimoto and Matthews at the University of British Columbia estimated, using Kepler data, that there could be as many as 6 billion Earth-like planets in the Milky Way alone. 6 billion. The number is enormous. It implies the galaxy is teeming with worlds. But the same galaxy that holds those 6 billion worlds also holds the 400 billion stars they orbit, and those stars are not arranged in a tight cluster. They are scattered across a flattened disk, 100,000 light-years wide and about 1,000 light-years thick. The average separation between neighboring stars in the disk near our position is about 4 to 5 light-years, meaning the galaxy, considered by volume, is overwhelmingly the volume of the space between stars, not the space of the stars themselves. The Milky Way is not crowded. The Milky Way is, by overwhelming majority, the dark between scattered grains of dust. Picture this. Shrink the entire Milky Way down to the size of the continental United States. At this scale, each star becomes a single grain of fine sand, barely visible to the naked eye. Our solar system and Alpha Centauri are 2 grains sitting about 4 inches apart. That seems reasonable. But the next nearest sun-like star, with a potentially habitable planet, might be a few feet away. A civilization 1,000 light-years distant would be in a different state entirely. 5,000 light-years would place them across the country. The full extent of the galaxy stretches from coast to coast. The galaxy looks crowded on a poster. In reality, it is defined by the emptiness between the grains. Most of the map is blank. Most of the space contains nothing at all. If intelligent civilizations exist on 6 billion worlds, they are distributed across this map, with hundreds or thousands of light-years between any 2 of them on average. Even a generous estimate of alien abundance places most civilizations at distances that are functionally unreachable. There is a temptation, looking at 6 billion habitable worlds, to assume that intelligence must arise on a substantial fraction of them, and that the galaxy must therefore be densely populated. The arithmetic does not actually support that intuition. Even if intelligent civilizations arise on 1 in every million Earth-like planets, an extraordinarily generous estimate by historical standards, that still leaves 6,000 civilizations in the galaxy. 6,000 civilizations scattered across 100,000 light-years of disk. The average distance between any 2 of them, assuming a roughly even distribution through the disk volume, works out to several hundred light-years. If civilizations are rarer, 1 in a billion, say, then there are 6 in the entire Milky Way, separated, on average, by tens of thousands of light-years. The number of civilizations matters less than the geometry, because the geometry is the constraint that ensures isolation, no matter how the number turns out. This is a different intuition from the one casual science fiction encourages. In most stories, the galaxy is a community. The various species know each other, trade with each other, sometimes fight each other. In the actual physical Milky Way, the species would not know each other exist. Even if 1,000 civilizations bloomed simultaneously across the galactic disk tonight, the light from each one would take centuries or millennia to reach any of the others, and by the time the light arrived, the civilizations would have either changed beyond recognition or vanished. The galaxy is not a community. The galaxy is a sequence of brief, unrelated flashes, scattered across a volume so large that no flash can light any other. Seen Voyager 1 at the 1 light day milestone, 2026. Imagine a small room in Pasadena, California. The walls are lined with monitors, the kind that have not been replaced in 20 years because the people who built them have retired, and no one quite knows how to update them without breaking something. On the largest screen, a number is climbing, 24 billion kilometers, and counting. The number represents the distance to a spacecraft launched in 1977, when most of the engineers in this room had not yet been born. The signal arriving on the screen is 22.5 hours old. The probe itself, in this moment, is not where the data says it is. It has moved on. The light from its transmitter is still in transit, crossing the gap between there and here at the only speed the universe permits. By the time the engineers in this room read the new telemetry, the probe will already be hours further out, still moving, still flying, still alone. It will cross the symbolic one-light-day mark this year. It has covered 0.06% of the way to the nearest star in 48 years of continuous outbound flight. The next 99.94% would take 73,000 more. The engineers stare at the screen. The number keeps climbing. The room is very quiet. Part 4. The second wall is energy. Distance is a passive obstacle. It simply exists, waiting to be crossed. What makes the crossing functionally impossible is what physics demands in exchange for speed. Because the only way to shrink an interstellar journey from millennia into something even remotely approachable is velocity. And velocity at the scales required for star travel costs energy in quantities that would bankrupt entire worlds. This is not a soft barrier. This is not a problem that a bigger engine or a better fuel source gradually solves. The energy requirements for interstellar travel scale in ways that are fundamentally hostile to engineering. They do not grow linearly with speed. They grow exponentially, and that exponential curve is not a feature of our current technology. It is a feature of the universe itself, baked into the equations of special relativity and confirmed by every particle accelerator ever built. Let us begin with the cheapest possible interstellar mission anyone has ever seriously proposed. A small robotic probe, no crew, no life support, no return capability. Call its mass 1,000 kilograms, roughly the mass of a small car. Now accelerate it to 10% of the speed of light. 10% of the speed of light is a common benchmark in serious interstellar discussions because it brings the travel time to Alpha Centauri down from 73,000 years to about 42 years, which is at least within a single human lifetime. At 10% of light speed, a spacecraft would be moving at roughly 67 million miles per hour. That is 150 times faster than the fastest object humanity has ever built relative to the Sun. To accelerate 1,000 kilograms to 10% of light speed requires approximately 4.5 times 10 to the 17th joules of kinetic energy. That is 450 quadrillion joules. The number means nothing in isolation, so let us anchor it. A large nuclear power plant produces roughly 1 gigawatt of continuous power. That is 1 billion joules per second. Running that plant at full capacity for one entire year produces approximately 3.15 times 10 to the 16th joules. So accelerating our tiny probe to just 10% of light speed would consume roughly 14 years of one nuclear power plant's total output. 14 years of a facility that cost billions of dollars to build, 14 years of the power output that lights 1 million homes, funneled entirely into pushing a car-sized object up to a velocity that still means a 42-year trip to the nearest star. Widen the lens. The total energy humanity produces in a single year, from every power plant, every engine, every fire, every solar panel on Earth, amounts to roughly 6 times 10 to the 20th joules. The energy needed for our small probe at 10% of light speed is approximately 1/1300th of global annual energy production. For a single car-sized probe with no deceleration capability, no crew, no return trip, just a small machine flung into the void with enough velocity to reach the nearest star in 4 decades. The Hiroshima bomb released approximately 6.3 times 10 to the 13th joules. The kinetic energy of our modest probe at 10% of light speed is equivalent to roughly 7,100 Hiroshima bombs, 7,000 nuclear detonations compressed into the motion of a single small spacecraft. That is the energy price for the cheapest possible interstellar ticket. Not for a crewed vessel, not for a round trip, not for a journey to a distant star, just a tiny probe aimed at the nearest one with no way to stop when it gets there. And we have not yet paid for stopping. A probe that arrives at Alpha Centauri at 10% of light speed will fly past the star system in a matter of hours unless it decelerates. Deceleration requires the same energy as acceleration applied in reverse. The energy budget just doubled. 14,000 Hiroshima bombs worth of energy for a small robot to visit the nearest star and come to a halt when it arrives. This is the scale of the problem for the simplest conceivable interstellar mission, and every subsequent number is worse. The fundamental constraint behind these numbers has a name. It is called the tyranny of the rocket equation. The Russian mathematician Konstantin Tsiolkovsky derived it in 1897, and it has been the silent governor of every spaceflight since Sputnik. The equation states a brutally circular relationship. To go faster, a rocket needs more fuel. More fuel means more mass. More mass means the rocket needs even more fuel to accelerate the additional fuel, which adds more mass, which requires more fuel. The feedback loop does not scale linearly with desired velocity, it scales exponentially. For chemical rockets, which produce exhaust velocities of roughly 4.5 kilometers per second, reaching even 1% of light speed would require a fuel-to-payload ratio so absurd that the spacecraft would need to be almost entirely fuel. Reaching 10% of light speed with chemical propulsion is not impractical. It is mathematically excluded. The amount of fuel required exceeds the mass of the observable universe. This is not a poetic exaggeration. The exponential function grows that aggressively. It is worth pausing on the word exponential, because exponential is one of those words that gets used in casual conversation to mean roughly the same thing as fast, and the technical meaning is much harsher than the casual meaning. When the rocket equation says fuel mass scales exponentially with desired velocity, it means that doubling the desired velocity does not double the fuel required. It squares it, roughly. Tripling the velocity cubes it. Going from 1% of light speed to 10% of light speed does not mean 10 times the fuel. It means a number so large that for chemical rockets the fuel requirement crosses the mass of the Earth, the mass of the Sun, the mass of the Milky Way, and the mass of the observable universe in fairly short order. The exponential curve does not climb politely toward a high ceiling. It vertically asymptotes. There is no amount of clever engineering of chemical propellants that walks back the exponent. The exponent is set by the math, and the math is set by the conservation of momentum, and the conservation of momentum is set by the symmetries of physical law itself. You are not arguing with the engineer when you try to do better. You are arguing with the universe. And there is one more layer to the energy wall that engineering cannot soften, because it is geometry. According to special relativity, as a massive object accelerates toward light speed, its effective mass increases. This is not a metaphor or a measurement artifact. The object literally requires more energy to accelerate each additional unit of speed. At 90% of light speed, a spacecraft's relativistic mass is approximately 2.3 times its rest mass. At 99% of light speed, roughly 7 times its rest mass. At 99.9% of light speed, more than 22 times. The closer you approach light speed, the more the universe resists your acceleration, demanding exponentially more energy for each incremental gain. Reaching light speed itself would require literally infinite energy. Not a very large number, mathematical infinity. It cannot be done. Not by us, not by any civilization made of matter, not now, not ever. Part 5. Every solution fails the energy flaw. If chemical rockets cannot do it, the natural next thought is nuclear. Surely a more powerful energy source can overcome what chemistry cannot. It is worth understanding why this is. Nuclear fission, the kind of reaction that powers a conventional nuclear power plant or a fission bomb, releases about 1 million times more energy per kilogram of fuel than the most efficient chemical combustion. That sounds enormous, and it is, but the exhaust velocity of any propulsion system based on it is still bounded by how fast the reaction can eject material out the back. A fission reaction, even an extremely well-contained one, produces exhaust at velocities of perhaps a few tens of kilometers per second when channeled through a thermal rocket nozzle. That is many times better than chemical rockets, which top out around 4.5 kilometers per second. It is still not within the same regime as the velocities required for interstellar travel. The energy density of the fuel is dramatically better. The velocity at which that energy can be turned into directed motion is only modestly better. The rocket equation does not care about energy density. It cares about exhaust velocity. And the exhaust velocity of any reaction is limited by the speed at which the products of the reaction can be expelled, which is set by the physics of the reaction itself. The history of seriously proposed nuclear interstellar concepts is sobering. Nuclear thermal rockets, which heat propellant by passing it through a fission reactor, achieve exhaust velocities roughly twice those of chemical rockets. That is meaningful for trips to Mars, useless for trips to other stars. The most ambitious nuclear propulsion concept ever seriously proposed was Project Orion, conceived at General Atomics by Freeman Dyson and Ted Taylor between 1958 and 1963. Project Orion would have detonated successive nuclear bombs behind a heavily armored pusher plate, using the explosions themselves as propulsion. The design was internally consistent. Dyson estimated that an Orion vehicle equipped with pure deuterium fusion devices at 25% energy efficiency could reach a top speed of about 10,000 kilometers per second, or 3.3% of the speed of light. 3.3% of light speed sounds promising until you realize the trip to Alpha Centauri would still take roughly 127 years one way, and the spacecraft would need to be the size of a city carrying tens of thousands of nuclear bombs as fuel. The project was set aside in 1963, and the Partial Test Ban Treaty of the same year made any further development effectively impossible. Fusion propulsion is the next theoretical step. If engineers could build a working fusion reactor that converts hydrogen into helium and channels the resulting energy into directed thrust, a fusion-powered starship could theoretically achieve exhaust velocities of several percent of light speed, making interstellar missions conceivable on timescales of centuries rather than millennia. Sustained controlled fusion remains beyond human capability, despite more than 70 years of dedicated research and hundreds of billions of dollars in global investment. The fundamental challenge is containment. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius, roughly 6 times hotter than the core of the Sun. At these temperatures, matter exists as plasma, a state so energetic that it destroys any physical container it touches. The most ambitious fusion experiment ever attempted is ITER, the International Thermonuclear Experimental Reactor, currently under construction in Cadarache, France. Its goals are limited, and its delays are instructive. ITER aims to demonstrate net energy gain, with an internal power gain factor of 10, for the first time in the history of fusion research. Its budget has climbed from roughly €5 billion at conception to more than €20 billion today. In July of 2024, ITER announced a major schedule revision. First, plasma at full current is now scheduled for 2034, deuterium-deuterium operations for 2035, and the deuterium-tritium burning plasma operations that actually demonstrate net fusion gain not until 2039. Another $5.2 billion was added to the cost. As of today, no fusion reactor on Earth has produced more energy than it consumed in a sustained, repeatable, continuous manner. The gap between the current state of fusion research and a working fusion-powered starship is not a gap that the next generation of engineers will close. It is a chasm spanning multiple fundamental breakthroughs, each of which may or may not turn out to be physically possible. The theoretical ceiling, the most energy-dense fuel that physics permits, is antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass into pure energy according to Einstein's equation. No other reaction in physics achieves this efficiency. Chemical combustion converts less than a 10 millionth of a % of fuel mass into energy. Nuclear fission converts roughly 0.1%. Nuclear fusion converts roughly 0.7%. Antimatter annihilation converts 100%. It is the ultimate fuel, and it is still not enough to make interstellar travel easy. To accelerate a 1,000 kilogram probe to 10% of light speed using pure antimatter propulsion would require roughly 500 kilograms of antimatter combined with 500 kilograms of normal matter. That sounds almost manageable until you learn how much antimatter the human species has produced in its entire history. Since 1995, CERN has produced about 10 nanograms of antihydrogen. 10 nanograms. A nanogram is 1/1000th of a gram. CERN's antiproton production rate is approximately 1.67 nanograms per year. If you gathered together every atom of antimatter that every accelerator on Earth has ever produced across every country over every decade of particle physics research, the resulting speck would not be visible to the naked eye. It would not register on a kitchen scale. It would not register on most laboratory scales. NASA's 1999 cost estimate for antihydrogen put the price at $62.5 trillion per gram. At current production rates, manufacturing a single gram of antiprotons would require continuous production at the current rate for roughly 600 million years, at a total cost of approximately 2.5 times 10 to the 15th euros. Producing 500 kilograms of antimatter is not a challenge for the next century or the century after that. It sits so far beyond current capability that placing a meaningful timeline on it is itself meaningless. The newest alternative to onboard fuel, and the one most discussed in the past decade, is laser propulsion. The idea is elegant. The spacecraft carries an extremely lightweight reflective sail. A ground-based or space-based laser array fires a coherent beam at the sail. Photons bounce off the sail, transferring momentum, and the craft accelerates. No onboard fuel required. The energy source stays at home. In 2016, the Breakthrough Starshot Initiative announced exactly this approach. The plan envisioned a fleet of gram-scale chip probes propelled by a ground-based laser array with a combined output of 100 gigawatts. 100 gigawatts is roughly the electrical generating capacity of a medium-sized country like the United Kingdom. That entire national-scale energy output focused into a coherent laser beam aimed at a sail smaller than a bedsheet would accelerate a 1-gram probe to 20% of light speed, reaching Alpha Centauri in roughly 20 years. 1 gram. Not a crude vessel, not even a useful robotic probe, a chip-sized sensor package weighing less than a paperclip. And as of 2025, the project has effectively stalled. Scientific American published a piece titled "The Quiet Demise of Breakthrough Starshot" earlier this year, reporting that the program has spent only about $4.5 million of the $100 million initially promised by its billionaire founder, and that the laser, sail, and beam steering challenges remain firmly in the research phase. Even if Starshot eventually flies, the architecture has a fundamental flaw the engineering cannot fix. The laser can only push, it cannot pull. A light sail, accelerated to 20% of light speed, has no way to slow down at its destination. It would scream past Alpha Centauri in a matter of hours, taking a few blurry photographs before vanishing into the interstellar void. To decelerate, you would need a second laser array at the destination. which would require that someone has already been there to build it, which means you have not solved the problem. You have assumed it away. There is a deeper version of this argument worth naming. Some readers will say, fine, current physics blocks every approach we have tried, but a sufficiently advanced civilization will discover physics we have not yet imagined. The argument is appealing because it cannot be falsified. By definition, we cannot disprove the existence of physics we have not yet discovered. But the structure of the argument is also unstable. Special relativity has been tested across more than a century. In every experiment, humans have been clever enough to design, and it has held. General relativity has been tested through gravitational lensing, the precession of Mercury, the timing of binary pulsars, the operation of GPS satellites, and the detection of gravitational waves, and it has held. Quantum field theory has been tested through the discovery of every particle in the Standard Model, through the operation of every transistor and laser and medical imaging device ever built, and it has held. The energy bound on interstellar travel does not depend on a single experiment or a single theoretical claim. It depends on the consistent, accumulating, multi-decade confirmation of the underlying physical framework. Future physics may surprise us in ways that change other questions, but the probability that future physics overturns the relationship between kinetic energy, mass, and the speed of light is comparable to the probability that future biology overturns the central dogma of molecular biology. Not zero, but small enough that building an argument on it is not open-mindedness. It is hope dressed as humility. Every propulsion concept ever seriously proposed for interstellar travel runs into the same fundamental constraint. Moving mass across light years requires energy on scales that are staggering by any civilizational standard. The specific numbers vary, but the underlying reality does not. Interstellar travel demands energy expenditures so vast that they represent a significant fraction of a civilization's entire energy budget, sustained over periods of years or decades, directed at a single mission with no guarantee of return. The barrier is not technology. The barrier is reality. Part 6. The third wall is time. Even if the energy bill could somehow be paid, the third constraint waits patiently behind the first two. Time, unlike distance and energy, cannot be compressed or stored or rationed. It simply passes. And it passes for everyone, including the would-be travelers, including the civilization that launched them, including the ship itself. Begin with the most generous case. 10% of light speed represents an ambitious but theoretically conceivable velocity for interstellar travel. At this speed, a spacecraft covers roughly 67 million miles per hour, fast enough to cross Earth's orbit around the Sun in under 3 hours, fast enough to traverse the entire solar system from the Sun to Neptune in roughly 2.5 days. By any human standard, 10% of light speed is blinding. And yet, at 10% of light speed, a journey to Alpha Centauri takes 42 years. One way. Not round trip, just getting there. A crew that departs Earth at age 30 arrives at age 72, assuming nothing goes wrong, assuming the ship functions flawlessly for over 4 decades, assuming the human body endures deep space for that long without catastrophic degradation. The return trip doubles the timeline to 84 years. The mission to the closest possible star and back would consume nearly an entire human lifetime. The person who steps onto the ship is not the person who steps off. They have aged beyond recognition. Everyone they knew on Earth has aged with them or died. Their children have grown old. Their grandchildren have grown old. The world they left behind has changed in ways they cannot predict. And this is the best case. Alpha Centauri is the nearest star. Most stars in the Milky Way are not 4 light-years away. Scale the math accordingly. At 10% of light speed, a journey to a star 100 light-years away takes 1,000 years. A star 500 light-years away takes 5,000 years. A star 1,000 light-years distant takes 10,000 years. These are not travel times any individual can survive. They are not travel times any crew can endure. They are durations that exceed the lifespan of every empire, every religion, every language, and every cultural tradition that humanity has ever produced. 10,000 years ago, human beings had not yet invented writing. They had not built cities. They had not domesticated horses. The entire arc of recorded human civilization, every book ever written, every war ever fought, every scientific discovery ever made, fits inside the travel time of a single interstellar journey at 10% of light speed to a moderately distant star. Now, reduce the speed. 10% of light speed is extraordinarily ambitious. A more realistic velocity for a large crewed vessel, accounting for fuel mass and structural constraints, might be 1% of light speed. At this speed, the nearest star is 424 years away. A star 100 light-years distant requires 10,000 years. A star 1,000 light-years away requires 100,000 years. At 1% of light speed, interstellar travel does not merely challenge human timescales, it obliterates them. The journey durations enter geological territory. 100,000 years ago, our species was sharing the planet with Neanderthals. No human structure, institution, or technology has survived 100,000 years. Nothing we have built has lasted even a fraction of that time. The oldest known continuously inhabited human settlement is roughly 12,000 years old. The oldest documented continuous institution is perhaps 5,000 years old. 100,000 years is not a human timescale. It is an evolutionary one. Species change over such intervals. Continents shift. Ice ages begin and end. This is where the concept of generation ships enters the conversation. The idea is straightforward. If no individual can survive the journey, perhaps a population can. Build a vessel large enough to sustain a self-reproducing community across centuries or millennia. The original crew lives, reproduces, and dies aboard the ship. Their descendants continue the journey. Generation after generation is born, lives, and dies in transit until the final generation arrives at the destination. The concept is elegant in the abstract. In practice, it is a catalogue of cascading failure modes. Start with biology. A 2018 study by Marin and Belufi, published in the Journal of the British Interplanetary Society, calculated the minimum genetically viable founder population for a multi-generational voyage to Proxima Centauri b. Under strict assortative breeding rules and a 6,300-year voyage at 1.3% of light speed, the answer was approximately 98 individuals. A 2014 study by anthropologist Cameron Smith reached a more practical floor for safe, long-term success, citing roughly 14,000 settlers, with 10,000 as a workable, practical minimum once disease, demographic chance, and skill redundancy are factored in. Either number, 98 or 10,000, is a small town. Housing, feeding, and sustaining thousands of people in a closed environment for thousands of years requires a ship of staggering size and complexity. The mass of such a vessel pushes the energy requirements for acceleration into territory that makes the already impossible numbers we have been discussing look conservative. There is a social dimension to the population question that the biology cannot capture. A community of 10,000 people, sealed in a metal container for 10,000 years, would be subject to all the pressures that have torn apart smaller, more accessible communities over much shorter time spans throughout human history: religious schisms, political factions, generational rebellions, resource hoarding, the slow drift of language, of custom, of memory. The cumulative effect of every social pressure that ordinarily produces collapse on a timescale of centuries, applied here without the safety valve of emigration, immigration, or external mediation. There is no court of appeal beyond the ship itself. There is nowhere to leave for. There is no fresh population entering to refresh the cultural memory. Everything that happens aboard happens in a closed loop with itself, multiplied across generations who never knew anyone outside their own corridors. The biology says a population that large could survive genetically. The history of human social organization suggests that the population that survives, by year 10,000, would not be the population that boarded. Population size is only the first problem. A closed ecosystem must recycle all resources perfectly: water, air, food, waste. Every molecule must be accounted for and reprocessed indefinitely. No closed ecological system has ever been sustained by humans for more than a few years. Biosphere 2, the most ambitious attempt at a sealed ecosystem in human history, lasted 2 years before oxygen levels dropped from 20.9% to 14.5%, and the system required external intervention. Biosphere 2 involved 8 people in a 3-acre enclosure on the surface of Earth with sunlight, a functioning magnetosphere, and access to emergency outside resources. A generation ship would need to sustain thousands of people in a sealed metal container hurtling through a vacuum, with no sunlight, no natural gravity, no magnetic shielding, and no possibility of outside help for thousands of years, without a single critical system failure. There is one more category of constraint that deserves attention here, because it transforms the abstract distance problem into a hostile physical environment. The space between stars is functionally empty by terrestrial standards, but at relativistic speeds, even near empty becomes lethal. The interstellar medium has a density of roughly 1 hydrogen atom per cubic centimeter in the warm neutral medium of the galactic disk, dropping to about 0.2 to 0.3 atoms per cubic centimeter inside the local interstellar cloud the Sun is currently passing through. By comparison, the air you are breathing right now contains about 25 quintillion molecules per cubic centimeter. The interstellar medium is roughly 25 quintillion times less dense than ordinary air. That is, by any human definition, empty. And yet, a spacecraft moving at 10% of light speed would plow through that emptiness at a speed at which even individual hydrogen atoms become projectiles. A 2017 study by Hoang, Lazarian, Burkhardt, and Loeb in the Astrophysical Journal, looking specifically at breakthrough Starshot-class probes traveling at 0.3 of the speed of light, calculated that the flow of hydrogen atoms hitting the forward face of the craft would exceed 3 times 10 to the 9th atoms per square centimeter per second. Every unshielded electronic component on the craft would degrade to inoperability within minutes. Beyond hydrogen, the interstellar medium contains scattered dust grains. A single 1 micrometer dust grain, at 10% of light speed, delivers a kinetic energy roughly equivalent to 1/10 of a milligram of TNT. A 100 micrometer grain at the same speed delivers energy equivalent to 100 grams of TNT. A single significant grain impact can compromise a vehicle, and over a journey lasting decades, the number of impacts accumulates. The void is not even passively empty. It is a slow, patient erosion at relativistic speeds. Shielding against this bombardment is theoretically possible, but adds mass, which adds energy cost, which adds back into the rocket equation, which the energy wall already cannot afford to pay. The arithmetic of mechanical reliability is its own quiet horror. A system with 99.9% annual survival probability, meaning a 1 in 1,000 chance of catastrophic failure in any given year, has only about a 0.005% chance of surviving 10,000 years without a single failure. Functionally, 0. To achieve even a 50% probability of intact 10,000-year operation, the annual failure probability must be less than 1 in 144,000. These are reliability levels that no human technology has ever approached. And they must be maintained not for a single system, but for thousands of interdependent systems operating simultaneously in the most hostile environment known, the void. Part 7. The ship outlives the civilization. Time does not only create logistical problems for the travelers, it creates a fundamental disconnect between the mission and the civilization that launched it. Consider a civilization that sends a crewed vessel toward Earth from a star 1,000 light-years away, traveling at 10% of light speed. The journey takes 10,000 years. During those 10,000 years, the home civilization continues to exist, evolve, and change. Technologies advance, social structures transform, values shift. The civilization that launched the mission 10,000 years ago may bear no resemblance to the civilization that exists when the ship arrives. It may have collapsed entirely, leaving behind ruins and silence. It may have transformed into something unrecognizable to the original planners. It may have developed faster propulsion technologies and sent a second mission that arrives before the first one. The ship becomes an artifact, a relic of an obsolete era, still crawling toward its destination, while the civilization that built it has moved on or disappeared. This is not speculation. It is extrapolation from observed patterns. Human technological capability has increased exponentially over the past few centuries. If this pattern holds for any expanding civilization, a mission launched today using the best available technology will be obsolete long before it arrives. A civilization that launches an interstellar mission faces a paradox sometimes called the incessant obsolescence postulate. If they wait, their technology improves and a future mission could arrive sooner. But if they always wait, they never launch. And if they launch now, the mission may be overtaken by a faster ship launched centuries later. The optimal strategy is always to wait for better technology, but waiting indefinitely means never going at all. The galaxy may be full of civilizations that always meant to send a ship and never did. Communication delay compounds every one of these problems into something approaching total futility. At interstellar distances, the speed of light imposes a hard limit on information transfer that is just as absolute as the speed limit on physical travel. A radio signal or laser communication beam travels at light speed. A message sent from Earth to a star 100 light-years away takes 100 years to arrive. A reply takes another 100 years to return. A single exchange of information requires 200 years. Imagine what a 200-year conversation actually looks like in practice. A civilization launches a mission to a star 100 light-years away. 10 years after departure, the home world discovers a critical design flaw in the ship's radiation shielding. They transmit a warning with detailed repair instructions immediately. That message, traveling at light speed, chases the ship across the void. The ship is also moving at 10% of light speed in the same direction. The message gains on the ship gradually, at the relative speed of 90% of c. It takes roughly 11 years to catch up. By the time the crew receives the warning, they have been flying with degraded shielding for 21 years. The cumulative radiation exposure may have already caused irreversible biological damage. The repair instructions reference tools and materials that were available at launch but have since been consumed or repurposed. The crew sends a reply explaining their situation and requesting alternative solutions. That reply takes over 11 years to reach home. The engineers who discovered the original flaw are now 32 years older. Some have retired, some have died. The institutional knowledge needed to devise an alternative solution may have migrated to a new generation of engineers who are unfamiliar with the ship's specific configuration. They develop a workaround and transmit it. Another 11 years pass. By the time the crew receives the revised instructions, more than 50 years have elapsed since the original flaw was discovered. The crew members who first received the warning are elderly or dead. Their replacements must interpret instructions written for a version of the ship that has been modified and repaired many times in the intervening decades. This is what interstellar communication looks like at 100 light years. Not a conversation, a series of messages in bottles, each one arriving too late to matter, each one referencing a reality that no longer exists. At 1,000 light years, the situation becomes absurd. A single exchange of information requires 2,000 years. The civilization that sent the original message may not exist when the reply arrives. The language the message was written in may have evolved into something unrecognizable. The communication channel itself, the frequency, the encoding, the protocol, may have been abandoned centuries ago, replaced by technologies the original senders never imagined. The reply arrives to an audience that cannot read it, transmitted by a sender that no longer exists, about a problem that was either solved or made irrelevant millennia before the response was composed. For a mission in transit, communication delay means total autonomy from the moment of departure. For all practical purposes, a ship traveling to a star 1,000 light years away cannot receive updated instructions from home in any meaningful time frame. Within a few decades, the lag renders real-time coordination impossible. Within a few centuries, even slow exchanges become impractical. The mission is on its own. Every decision must be made locally. Every problem must be solved without external help. Every crisis must be managed by the crew or by the ship's autonomous systems, with no possibility of consultation, reinforcement, or rescue. The ship becomes an isolated civilization unto itself, severed from its origin permanently. If the ship encounters a catastrophic problem, no one is coming. If the mission succeeds, no one from the launching civilization may be alive to receive the news. Consider the cumulative effect of communication delay across the lifespan of a mission. A starship launched on a 1,000-year voyage receives, over the first century, perhaps a few hundred messages from home. The messages from the second century arrive less frequently, because by then the launching civilization has had 100 years to lose interest, change political systems, and reallocate its attention. By the 3rd century, the messages are sporadic. By the 5th century, they have effectively ceased. The mission was a project of a generation that no longer exists. The institutions that funded it have been renamed twice. The communication protocols the original team designed have been deprecated by the engineers who replaced them. The mission keeps flying. The crew continues to perform the work the founders specified. The ship is moving outward through space, and nobody on Earth is listening anymore. The crew may not know this for decades, because the absence of new messages from home is not, in real time, distinguishable from a temporary lull. By the time the crew accepts that the silence is permanent, they have lived inside it for half a generation. This is a different kind of failure mode than the ones engineers usually plan for. It is not a mechanical failure. It is not a navigational failure. It is a relational failure. The mission was launched as a relationship, sender and receiver, home and travelers, civilization and explorers. The relationship cannot survive the timescales the geometry imposes. It atrophies over decades, dies over centuries, and is forgotten over millennia. The ship continues, the mission continues. But the meaning of the mission, the thing that made it a mission, rather than just a piece of metal moving through space, depends on a connection to home that the physics of the journey makes impossible to maintain. And so the journey unfolds in a kind of permanent silence. The ship moves outward through empty space. The crew, or their descendants, continue their work. The homeworld recedes behind them in time as well as space. By the time they arrive, the people who sent them are dust, the institutions that funded them are forgotten, and the stars that hung in the sky over the launch ceremony have moved across the heavens. The ship arrives, if it arrives at all, as an artifact of a dead culture, carrying instructions from senders who could not have anticipated what the universe would have done to them while they were in transit. Part 8. 5,000 years aboard. Scene Generation Ship, year 5,000 of a 10,000-year voyage. Walk the corridor. The lights are dim by design. Calibrated for the half-dark sleep cycle the inhabitants have observed for hundreds of generations. But you do not need bright light to find your way. The corridor curves gently along the inner circumference of the great rotating hull, and you know its geometry the way your distant earth-bound ancestors knew the shape of the rooms they were born in. The air has the faint metallic smell of constant recycling, a smell that has been in your nose since the day you were born, a smell no one aboard finds notable because no one aboard has ever smelled anything else. 2 children pass you, running on the slight downhill of the curve, their laughter echoing off the curved walls. In a meeting chamber halfway around the ring, the council is debating water again, the third crisis of the century. The desalinization beds in the lower agricultural deck began producing brackish output 6 months ago, and the engineer's cast, which has carried the responsibility for the ship's life support systems through approximately 160 generations, has not been able to identify the cause. The original schematics, scanned into the central archive at launch, refer to a manufacturer on Earth that no one has heard of in 5,000 years. The replacement parts they were told to use can be synthesized aboard, but the equipment that synthesizes them is itself half a century overdue for refurbishment. The Council debates the priority order. The chief engineer, a woman whose family has held this position for 9 generations, speaks slowly and patiently, the way her great-great-great-great-grandmother taught her. In a chamber 2 decks below, a different conversation is happening. A small group of philosophers, who in any other society would be called priests, are arguing about the destination. 3 rival cosmologies have hardened over the past few centuries. One holds that the mission is sacred, a divine mandate inherited from ancestors who saw a truth the present generation must honor. Another holds that the mission is a prison sentence imposed by long-dead tyrants who had no right to condemn their descendants to life inside a metal tube. A third has developed a religious framework that reinterprets the journey entirely, teaching that the ship has always existed, that the idea of an origin world is a comforting myth, and that the concept of a destination is a heretical fantasy designed to distract the faithful from the only reality that matters. The ship itself, the original crew, is 20 generations dead. Their names survive in a database that fewer and fewer people consult with each century. There is a memorial hall in the upper deck where holograms of the founders flicker softly, but it is rarely visited. Most of the children passing you in the corridor have never seen a sky. Many have never seen liquid water in a container larger than a personal cup. The idea of weather is taught as a chapter in the history curriculum alongside the names of the founding scientists and the orbital mechanics of a distant solar system that may or may not still contain the planet the mission was sent to study. The destination is half the journey away, a star whose light is the same to the children aboard as any other point on the navigation display. 5,000 more years to go. Most of the people in the corridors around you understand that the destination, like the origin, is more concept than fact. It is something the Council reaffirms each year. Something the engineers calculate trajectories toward. Something the philosophers argue about. The ship is the only world anyone has ever known. Walk further. The corridor opens into a small park, designed 2,000 years before your birth, where the lights brighten gradually to simulate dawn over a meadow that no person aboard has ever seen in life. The grass underfoot is real grass, descended from samples brought up from the homeworld at launch, modified across hundreds of generations by the ship's botanists to survive the cycle of artificial seasons. A small stream runs through the park, recycled from the agricultural decks, and returned to them after passing through the gravity-fed loops the founders designed. Children play here in the afternoon. Some of them are studying for the engineer's cast exams. Others are training for the philosopher's cast. A few are simply running because they are 8 years old and the park is large enough to run in and the light overhead suggests morning. You sit on a bench. A woman sits down beside you. She is perhaps 60 years old by the ship's calendar, which is a slightly different calendar from the one Earth still keeps. Recalibrated 3,000 years ago, after a long council debate about whether the original Earth calendar still meant anything aboard. She is a navigator. She tells you, in the patient way that older shipboard people tell visitors things, what her work involves. She is calculating course corrections that will be needed in another 1,800 years. She will not be alive to see them executed. Her great-grandchildren will execute them, if they decide the destination is still worth aiming for. She is not sure they will. She is not sure she would, in their position. She tells you that her grandfather, who taught her the navigation tables, often said that the work was a gift to people you would never meet, and that the gift was worth giving even if the people decided not to use it. She tells you that she has come to believe him. She looks up at the artificial sky overhead, the panels that dim and brighten on the cycle the founders set. She says that her favourite part of the day is the moment just after the morning light comes on, when the air still smells faintly of the night cycle and the children have not yet started running. It is the closest thing she will ever know to a dawn. She has read books about the dawns on the homeworld. She has watched the archival footage. She knows, intellectually, that she is missing something her ancestors took for granted. She does not feel the loss, the way the books say her ancestors would have. She has had her whole life to make peace with what the ship does and does not contain. The ship is the only world anyone has ever known. The barrier is not technology. The barrier is reality. Part 9. The Standard Rebuttal. There is one argument that always surfaces at this point in the conversation. It looks at the distance, the energy, and the time, and it says, you are thinking too small. You are projecting human limitations onto alien civilizations. A civilization millions of years more advanced than us would have technologies we cannot imagine. They would find ways around these barriers that we are too primitive to even conceive of. They would simply be more advanced. The argument has an intuitive appeal. It feels humble. It feels open-minded. It feels like it respects the vastness of possibility. It is the kind of thought experiment a curious person would entertain at the end of a long evening, when the night sky is full and the question of who else might be out there feels too large to resolve. The argument needs to be taken seriously before it can be set down. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations based on their total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16th watts, for an Earth-sized world. A Type 2 civilization harnesses the entire energy output of its host star, roughly 4 times 10 to the 26th watts, for a Sun-like star. A Type 3 civilization harnesses the energy output of its entire galaxy, roughly 4 times 10 to the 36th watts, for a Milky Way-sized galaxy. Humanity currently sits at approximately 0.7 on this scale. We do not yet capture all the energy reaching Earth from the Sun, let alone the Sun's total output. The Kardashev scale is often invoked to suggest that sufficiently advanced civilizations would find interstellar travel trivial. A Type 2 civilization commanding the full power of a star should be able to launch starships the way we launch satellites. A Type 3 civilization, harnessing an entire galaxy, should be able to scatter probes across the cosmos like seeds on the wind. The energy wall described earlier in this video, the argument goes, would crumble before such staggering power. This is the argument in its strongest form. It deserves an honest hearing. Imagine a civilization that has, over millions of years, fully encircled its home star with a Dyson sphere, a constructed shell or swarm that captures every photon the star emits. Imagine that civilization's launch pad, where their next interstellar probe is being prepared. The energy budget for the launch is displayed on a wall. The probe will consume a meaningful fraction of 1 day of their stellar output. 1 day of the entire energy output of a star. The probe will accelerate, coast for several centuries, and arrive at its target star system. The civilization has done what no human technological tradition could even contemplate. They have made a sustained interstellar program viable. Now consider what has actually happened. They have not made the trip cheap. They have not made it short. They have made it affordable in their economy by accessing a much larger energy budget than anything Earth could ever produce. They can launch many such missions. Each one still takes centuries. Each one still arrives at a destination that may have changed unrecognizably during the journey. Each one still faces the dust, the radiation, the mechanical degradation, and the slow erosion of mission relevance. They have changed the size of the checkbook. They have not changed the size of the check. And there is another category of proposed solution that goes further. It says, perhaps the answer is not more energy, but different physics, warp drives, wormholes, faster than light travel. These concepts populate science fiction with such regularity that many people assume they represent genuine scientific possibilities, awaiting only sufficient technological advancement. So this is the question that needs an honest answer. Are they real? Could a sufficiently clever civilization sidestep the speed of light? Part 10. The energy flaw is universal. The honest answer is that current physics gives us no path. And the reasons matter because they are not engineering reasons. They are structural reasons. The speed of light is not a velocity limit in the way that a speed limit on a highway works, where you could theoretically build a faster car, but choose not to. It is a structural feature of how space and time relate to each other. The kinetic energy required to accelerate any object increases with the square of its velocity, and relativistic effects compound the problem as velocity approaches c. As any massive object approaches light speed, the energy required to accelerate it further approaches infinity, not a very large finite number, actual mathematical infinity. You cannot reach infinity. You cannot exceed it. You cannot engineer around it. The speed of light is the geometry of the universe, and you cannot build a machine that violates geometry. Could future physics reveal something unexpected? In principle, yes. Any scientific conclusion is subject to revision in light of new evidence. But the probability that future discoveries will overturn the speed of light limit is comparable to the probability that future biology will overturn germ theory. Not zero, but so close to zero that building an argument on it is not open-mindedness. It is wishful thinking wearing the costume of humility. Special relativity has been confirmed by every experiment ever designed to test it, across more than a century. General relativity has been confirmed by gravitational lensing, gravitational waves, the precession of Mercury's orbit, the behavior of GPS satellites, and hundreds of other observations. In 2007, Muller and colleagues constrained possible Lorentz invariance violations to a precision better than 1 part in 10 to the 18th using rotating optical resonators. In 2009, the Fermi Gamma Ray Space Telescope's observation of gamma ray burst 090510 bounded any energy-dependent speed of light variation to better than 1 part in a Planck mass. In 2017, LIGO's detection of the binary neutron star merger GW170817 confirmed that gravitational waves and light travel at the same speed to 1 part in 10 to the 15th. But what about the proposed solutions that do not, in principle, require breaking the speed of light? What about warp drives? The Alcubierre metric, first formalized by physicist Miguel Alcubierre in 1994, proposes contracting space in front of a vessel and expanding it behind, creating a bubble of warped spacetime that carries the ship faster than light without the ship itself exceeding light speed through its local space. The mathematics are internally consistent within general relativity. The original Alcubierre drive required exotic matter with negative energy density to sustain the warp bubble. No such material has ever been observed. The energy requirements in early calculations exceeded the mass energy of the entire observable universe. Later refinements brought it down to merely the mass energy of Jupiter, which remained, charitably, well beyond any conceivable engineering capability. In the past few years, the calculation has actually improved in a substantive way. In April 2024, Jared Fuchs, Christopher Helmerich, Alexei Bobrick, and Gianni Martier published a paper in Classical and Quantum Gravity titled Constant Velocity Physical Warp Drive Solution. Their result, building on earlier work by Bobrick and Martier in 2021, demonstrated that classic warp drive spacetimes can be made to satisfy all of the classical energy conditions, with no negative energy requirement, by combining a stable matter shell with a carefully chosen shift vector distribution. This is a real theoretical advance. It removes the original exotic matter sticker shock from Alcubierre's metric. It is honest physics, published in a respected journal, peer-reviewed. It is worth pausing on this paper for a moment, because it is being widely misrepresented in popular discussions of warp drives. Some commentators have read the result as evidence that warp drives are within engineering reach, or that the science fiction promise of fast interstellar travel is suddenly back on the table. Neither claim is accurate. The paper is genuine progress on a specific theoretical question, namely whether a warp metric can be constructed without violating the classical energy conditions. The answer is yes, it can. That is a real theoretical advance worth recognizing. There are 2 enormous catches. First, the solution is subluminal. It does not exceed the speed of light. It is a warp drive in the strict sense of the metric, but it does not deliver the science fiction promise of arbitrarily fast travel. Second, and this is the deeper limitation, every known positive energy warp solution requires pre-positioning matter along the entire flight path of the bubble. As Lobo and Visser showed back in 2004, you cannot use a warp drive to reach a star you have not already mapped and pre-stocked with the necessary mass distribution. The drive requires infrastructure to be set up everywhere you want to go before you go there. This is not how science fiction warp drives work. This is essentially a very expensive way to travel quickly along a route that someone else has already painstakingly built. What about wormholes? A wormhole, or Einstein-Rosen bridge, is a theoretical tunnel through space-time connecting 2 distant points. If stable, traversable wormholes could be created and maintained, they would indeed allow nearly instantaneous travel between distant locations. Every known solution to the equations of general relativity that produces a wormhole also requires exotic matter with negative energy density to hold the wormhole open. Without this material, the wormhole collapses faster than any object could pass through. The same exotic matter that has never been observed and may not be physically possible. In 2018, Juan Maldacena, Alexei Malekin, and Fedor Popov, and separately Maldacena and Key, published constructions for traversable wormholes in anti-de Sitter backgrounds that soften the exotic matter requirements. The wormhole becomes traversable through a clever double-trace deformation. But these constructions live in idealized ad spacetime, not in the actual universe we inhabit, and even in their idealized form, they do not permit superluminal signaling. And here is the deepest reason why faster-than-light travel of any kind faces the same structural obstacle. If any signal of any kind, by any mechanism, ever exceeded the speed of light between two inertial reference frames, the geometry of spacetime would automatically allow it to be reread as a signal traveling backward in time. This is not a paradox of bad imagination. It is the consequence of Lorentz invariance, written down by Tolman as early as 1917, refined by Benford, Book, and Newcomb in 1970, and reconfirmed by Liberati, Sonego, and Visser in 2002. The conclusion of every one of these analyses is the same. Any superluminal signaling channel reproduces what is called the Tolman tachyonic antitelephone. You can send a message into your own past. The universe responds by enforcing what physicists call the chronology protection conjecture, an as yet unproven but strongly supported principle that the laws of physics actively prevent the formation of closed time-like curves. The fact that we have never observed time travel paradoxes is itself, on this reading, the strongest evidence that the universe does not permit faster-than-light signaling. It is worth dwelling on the cleanness of this argument, because it tends to get lost in the technical details. Relativity does not say, faster-than-light travel is hard. It does not say, faster-than-light travel is expensive. It says, faster-than-light signaling between two reference frames is mathematically identical to a closed time-like curve, which is mathematically identical to time travel, which is mathematically identical to a logical contradiction. Any signal that exceeds c between inertial frames opens a route by which messages can be sent into their own past. The universe enforces causality through the geometry of spacetime itself. The chronology protection conjecture says, in effect, that the universe's bookkeeping is consistent. Information cannot exceed c, because if it did, it would arrive before it left, and the laws of physics would no longer admit a consistent history. The fact that we live in a universe with a consistent history is, on this argument, the universe quietly demonstrating that c is the speed limit. Every clock that has ever ticked has ticked in agreement with the principle that information stays inside the light cone. The principle is not a polite request. It is the way the geometry works. Seen, standing on the outer shell of a Dyson sphere. Stand on the curved metal surface and look outward. The stars of an alien galaxy fill the sky above you, but the brightest light comes from beneath your feet. You are walking on the surface of a constructed shell, kilometers thick, that fully encloses your home star. The civilization you belong to harvests every photon the star produces. Your annual energy budget is 400 million billion times the entire annual energy production of Earth. You can do almost anything that physics permits. Almost. In a launchpad complex, 1,000 kilometers away, the next interstellar probe is being readied. The ship is the size of a small moon, propelled by carefully channeled annihilation reactions, designed to accelerate for a decade and coast for 2 more centuries. Its destination is a star 300 light-years from your home, where your telescopes have identified an interesting world. The trip is the most ambitious mission your civilization has attempted in millennia. You look at the energy budget on the wall of the planning office. The launch will consume the equivalent of 1 full day of your star's total output, channeled and focused with 100% efficiency. 1 day of a star for 1 ship to 1 destination. The ship will arrive in roughly 315 years, and by then, your civilization will have changed in ways you cannot predict. The crew aboard will have lived their entire lives in a metal tube. The destination star, when they arrive, will have moved across the sky from where it appeared at launch, and this is the optimal case. This is what physics allows, even when you have built the largest power source the universe permits. The barrier is not technology. The barrier is reality. Part 11. The silence is consistent with both empty and full. If the energy wall is universal, and the time wall is universal, and the distance wall is universal, then the silence of the sky becomes a different kind of question. It is not, primarily, evidence about whether anyone is out there. It is evidence about the shape of the universe we live in. Two opposite worlds become empirically indistinguishable from Earth's vantage point. A universe that is empty of intelligence, and a universe that is full of intelligence that cannot ever physically meet. The physics of distance, energy, and time make these two universes look identical from where we are sitting. Michael Hart, in 1975, published a paper titled An Explanation for the Absence of Extraterrestrials on Earth. His argument was this: if intelligent civilizations exist anywhere in the Milky Way, even one of them, given a relatively modest velocity of 10% of light speed, would have colonized the entire galaxy in 650,000 to 2 million years. In 1980, the cosmologist Frank Tipler extended the argument by adding self-replicating probes to Hart's framework. Tipler calculated that even using existing spacecraft speeds, von Neumann probes that mine local materials at each new star system to build copies of themselves could spread across the galaxy in less than 300 million years. The galaxy is roughly 13 billion years old. The Earth has been habitable for the past 4 billion. Either timescale, Hart's or Tipler's, is many times shorter than the age of the galaxy. Therefore, the Hart-Tipler argument goes, if even one civilization had ever achieved interstellar capability, the galaxy should already be visibly colonized. It is not. Therefore, by the strongest reading of the argument, either civilizations are exceptionally rare, or all of them fail catastrophically before achieving expansion. The Hart-Tipler argument is the strongest version of the Fermi paradox, and it deserves to be sat with for a moment. It is not obviously wrong. The galaxy is old. Even slow self-replication, even at sub% of C, should fill the available volume in a small fraction of the galaxy's age. The silence is real, and on the Hart-Tipler reading, it is loud. But there is a serious counter-argument, published in 2018 by Anders Sandberg, Eric Drexler, and Toby Ord, titled Dissolving the Fermi Paradox. Their analysis points out that the Drake equation parameters that determine the expected number of civilizations are not single numbers. They are probability distributions, each with substantial uncertainty. When you multiply distributions rather than point estimates, the resulting expected value distribution becomes extremely wide. The Sandberg-Drexler-Ord result is that given honest uncertainty about each parameter, there is approximately a 40% probability that we are alone in the entire observable universe. Not just in the Milky Way, in every galaxy we can see. Not because aliens cannot exist, but because the probability distribution of the parameters is wide enough to put substantial probability mass on n equals 1. The Hart-Tipler reading and the Sandberg-Drexler-Ord reading are not actually opposed. They are answering different questions. Hart-Tipler asks, given that one civilization exists, why isn't the galaxy colonized? Sandberg-Drexler-Ord asks, how many civilizations should we expect to exist in the first place? Both questions, in their honest forms, return the same surface observation. The sky is silent. The interpretation depends on which question feels more pressing to you. The argument this video has built does not require either interpretation to be correct. The energy and time walls apply regardless of how many civilizations are out there. Even if Hart and Tipler are right, that a single colonizing civilization would have filled the galaxy by now, the energy flaw explains why no civilization may have ever launched in earnest. The cost of crossing interstellar distances is not merely high, it is universal. It applies to every civilization made of matter, and it has no engineering solution. Even if the Sandberg-Drexler-Ord interpretation is right, and intelligent civilizations are far rarer than we hoped, the energy and time walls explain why even the surviving ones would remain quietly inside their own home systems, indistinguishable from absence at interstellar distances. There is a separate dimension to the silence that deserves attention. Detection itself is harder than people often realize. Earth has been emitting strong radio signals into space for roughly 80 to 100 years, beginning with the early high-power radio broadcasts and continuing through television, military radar, and the modern leakage of countless terrestrial transmitters. The resulting bubble of detectable Earth signals expands outward at the speed of light, and so currently has a radius of about 100 light-years. That bubble of 100 light-years contains, by various estimates, somewhere between a few thousand and a few 100,000 stars, depending on how generous you are with the definition of detectable. It sounds like a lot of stars. It is also less than 1/1000th of 1% of the volume of the Milky Way galaxy. The bubble of Earth's existence, electromagnetically speaking, covers approximately 0.001% of our galactic disk. The other 99.999% of the galaxy is, from our point of view, a place where nobody has even heard of us yet. And our signals weaken with distance, according to the inverse square law. At 100 light-years, even a strong terrestrial broadcast is so attenuated that detecting it would require a receiver far more sensitive than anything humanity currently operates. At 1,000 light-years, the same signal is 1/10,000th as strong, lost in the noise of the cosmic background, indistinguishable from the natural radio emissions of stars and pulsars and the cosmic microwave background itself. The detection problem works in both directions. If alien civilizations are broadcasting, their signals weaken by the same inverse square law. By the time a typical broadcast from a civilization 1,000 light-years away crossed the gap to Earth, the signal would have spread across such an enormous volume of space that the energy arriving at any 1 square meter on Earth would be vanishingly small. To detect such a signal, we would need a receiver of impractical scale, tuned to the right frequency, listening at the right moment, while the signal travelled outward through a sky already filled with natural noise. The search for extraterrestrial intelligence has been listening seriously for about 60 years. The volume of sky it has surveyed at any meaningful sensitivity is, in galactic terms, a vanishing speck. And even within that surveyed volume, signals would need to be deliberately aimed at us and powerful enough to overcome the inverse square dilution between source and receiver. Most natural civilizational behavior, the kind of leakage Earth produces, is far too weak to be detected at the distances at which most civilizations would have to live to be there at all. The physics we have spent this video describing is consistent with both readings. It does not pick a side. It simply explains the geometry of a universe in which whatever civilizations exist are functionally separated from each other by walls that no engineering will ever take down. The silence is the surface. The walls are underneath it, and those walls are, from our vantage point, the same walls regardless of what is on the other side. Part 12. The Candle Flames in the Cathedral. Scene: a cathedral interior vast and dark. Step into a cathedral so large you cannot see its far walls. The ceiling vanishes into darkness above you. The floor extends outward beyond the reach of any light source you carry. The air is cold, the kind of cold that suggests a stone interior, but you cannot see the stones. You cannot see anything except the single dim point of your own held candle and a few others scattered in the distance. Walk forward. As you walk, more candles come into view. Small flames scattered across the floor at irregular intervals, each one casting a small circle of light around itself. Some of the candles are tall and freshly lit, their flames steady and bright. Others have burned low, their wax pooling, their flames flickering near extinction. A few are nothing but cooled wax and the faint smell of smoke, left over from candles that burned out long before you arrived. A few unlit candles wait, untouched, for someone who has not yet come. Each flame illuminates only its own small circle. The space between any two flames is dark. Walk to the nearest one and stand beside it. The flame is warm. The light it casts is real. The world it lights is small, perhaps the size of a few footsteps in each direction. Now turn and look at the next nearest flame. It is perhaps 50 meters away. The space between you and it is total darkness. The light from your candle does not reach it. The light from its candle does not reach you. The two of you exist in the same cathedral, but the cathedral is too large for either light to bridge the gap. Walk further. The pattern continues. Each flame is alone in its own circle of illumination. Some of the flames you can see in the middle distance are bright, some are dim, some are clearly about to go out. A few new ones flare into life as you walk, lit by no visible hand, burning briefly before extinguishing. The cathedral is full of flames. The cathedral is also empty of light. Both statements are true at the same time. This is the galaxy. The flames are civilizations. The cathedral is the Milky Way. There may be thousands of flames burning right now. There may be only a few. The cathedral does not care. It is too large. It is built to a scale at which no flame can ever reach another. The light each one casts is real and warm and small. The darkness between them is total. Some of the flames have already burned out. Some have not yet been lit. The ones that are burning now will burn for a brief time and then go out, and the cathedral will continue to exist around them, dark and patient and unchanged. You walk a little further, you realize that your own candle, the one you carry, casts its own small circle of light. You are one of the flames. The earth is the wax. Humanity is the wick. The cathedral is the same cathedral whether or not you are walking through it. The flames you can see from where you stand are the ones whose light has had time to reach you. The flames that have already gone out are still casting old light that you might be seeing right now, light that left them centuries ago, decades before they extinguished. The flames that have not yet been lit, you cannot see at all. You are in the cathedral with them. None of you can reach each other. None of you can speak to each other. None of you can touch. That is the picture. The night sky lies, and this is the truth underneath the lie. The universe is full of small, bright places, each one its own self-contained world, each one casting its own small circle of light. The space between them is not empty in the way the floor of an empty room is empty. It is empty in the way the silence of the cathedral is empty. It is the medium that defines the place. It is what the cathedral is made of, almost entirely. The flames are the exception. The dark is the rule. Part 13. What the universe is and is not. After 2 hours of physics, it is worth saying what this video has not been about. It has not been about whether aliens exist. It has not been about whether the Earth has been visited. It has not been about whether intelligent life is common or rare. It has not been about whether any of us will ever know the answer. Those are different questions, and they have their own difficult arguments. This video has been about something narrower and, perhaps, more permanent. It has been about the shape of the universe we live in, about what the laws of physics actually permit, regardless of how clever or patient or determined any civilization might be. It is worth stating this conclusion in the plainest terms available, because the implication is unusual enough to be worth landing slowly. Most of the conclusions science has produced about the universe over the past 4 centuries have been the kind of conclusions that improve human prospects. The Copernican revolution reorganized our place in the cosmos in a way that, while initially humbling, opened up a vastly larger universe to explore. The germ theory of disease saved billions of lives. The understanding of evolution put humanity into a coherent biological framework. Quantum mechanics gave us every modern electronic device. The interstellar travel conclusion is different. It is a conclusion that closes a door rather than opens one. It says, here is something we cannot do, ever, by any means, regardless of how clever we become. That is not a familiar shape for a scientific finding. Most scientific findings expand possibility. This one constrains it, and the constraint is permanent in a way that even the most pessimistic medical or environmental predictions are not, because medical and environmental predictions are subject to revision by new techniques. The interstellar constraint is set by the structure of space-time itself, which is not subject to revision by any technique. The shape is this: distance, energy, and time are not three separate obstacles. They are one obstacle expressed in three different units. They interlock. Distance demands speed. Speed demands energy. Energy is bounded by the geometry of space-time itself, and time consumes everything that distance and energy together require. The wall is not three walls. It is one wall, three sides of the same wall, all of them set by physical constants written into the universe, before any civilization existed to read them. The wall is the same height for every civilization, regardless of how advanced they are, because the constants do not change for advanced civilizations. The Kardashev scale gives more energy, not a smaller bill. The arithmetic does not bend to wishfulness or ambition or to the engineering of any species. This is a different kind of conclusion than the ones the universe usually offers. It is not hostile. Nothing in the physics we have walked through has been built to thwart life. The constants of the universe were not selected to keep civilizations apart. They simply have, as a side effect of their other functions, the property of making interstellar visitation effectively impossible. The universe does not prevent life from arising. It prevents life from meeting. It builds walls of light years between every inhabited world and enforces those walls with the most fundamental laws available: the speed of light, the conservation of energy, the arrow of entropy, the slow, patient passage of time. The realization should land calmly. It is not a defeat. It is not a tragedy. It is a description. It is the answer to a question physics has been quietly building for the past century, and the answer is not the kind of answer that arrives with fireworks or with grief. It arrives the way the conclusions of careful arithmetic always arrive, which is to say, without much ceremony. The numbers add up. The geometry is consistent. The walls are where they are. The cathedral is the cathedral. The candles are the candles. There is nothing in any of this that requires any species, anywhere, to feel any particular way about it. The universe was not built to console us about its dimensions. It was built, or rather, it just is, and the dimensions are what they are, and the conclusion follows from the dimensions, in the way conclusions always follow from premises. This is not the kind of finding that makes a press release. It is the kind of finding that, once you have sat with it for a while, simply becomes part of how you understand the place you live. The galaxy might be full of civilizations, each one in its own corner of the same cathedral, looking up at the same dome of pinpoints, maybe staring at the same unknowable question we are. Some of them, on planets we will never see, may have arrived at the same conclusion we are arriving at now. They may have done their own arithmetic. They may have built their own probes. Their probes may be drifting through their own interstellar voids right now, slowly losing power, never to arrive anywhere. They may have looked at the numbers and decided not to try. They may have looked at the numbers and decided to try anyway, and their effort may be unfolding right now across spans of time that exceed the lifespan of their species. We will not meet them. We probably will never know they were there. The light from their stars may already be reaching us tonight, indistinguishable from the light of stars that host no minds at all. This is, finally, the picture this video has been pointing at from the beginning. The universe is not arranged to introduce its inhabitants. It is arranged in a way that has the side effect of preventing introduction, and the side effect is comprehensive. Distance, energy, and time, working together, ensure that the flames in the cathedral burn in their own circles of light and never reach the next flame over. This is not a moral fact about the universe. It is a structural fact. The room is too large. The flames are too brief. The light each one casts is too weak to bridge the gap to its nearest neighbour. The cathedral was built this way, by no architect, by no plan, and the cathedral does not know that it is built this way. The cathedral simply is what it is. Some of the flames in the cathedral are already out, and the light that left them is still in transit. Some of the flames will not be lit until long after our own flame has gone. Whatever overlap exists, in time and in space, is statistically vanishing. There is a useful image for this, borrowed from astrophysicist Carl Sagan, who often pointed out that the universe is mostly a story about timing as much as it is a story about distance. Two civilizations that could, in principle, contact each other if they happen to overlap in time, may simply never overlap. The Milky Way is roughly 13 billion years old. Earth has been habitable for about 4 billion of those years. Intelligent life has existed on Earth for, generously, a few 100,000 years, and technologically capable intelligent life for about 200. The window during which any individual civilization is both alive and technologically broadcasting is, by every available measure, a small slice of its star's lifespan. Multiplied across the galactic timeline, the probability that two civilizations happen to be alive and broadcasting at the same moment in such a way that the signals from one could ever reach the other is mathematically small. Most civilizations, if they exist, do not overlap in time with any other civilization at all. They arise, burn briefly, and extinguish, and the next civilization arises long after the previous one has gone, and the gap between them is filled with the silent transit of stale electromagnetic radiation from worlds that are no longer there. The universe does not arrange its inhabitants to meet. It arranges them, by the geometry of its own construction, to be alone in their own skies. That is not a punishment. That is just the architecture. The barrier is not technology. The barrier is reality. Part 14. The sky still looks like a neighborhood. Go outside, if you can, on a clear evening after this video ends. Find a place where the city lights do not wash out the dark. Look up. Find two stars that appear almost touching. The same illusion will be there. The dome will still flatten everything into a painted ceiling. The pinpoints will still look like neighbors. The night sky still looks like a neighborhood. After 2 hours of physics, you can stand under the same stars and see the same lie, but you can no longer believe it. That is what this video was for. Not to argue you out of hope, or out of curiosity, or out of the deep human pull to imagine someone else looking back. Those instincts are good. They are part of what makes us pay attention to the sky in the first place. But the picture behind the picture is different now. The two stars that look almost touching are separated perhaps by 50 light years. Their light arrives together by coincidence of geometry, and your eye accepts the coincidence because your eye was not built for the truth. The truth is 25 trillion miles to the nearest one, 73,000 years at our fastest probe's current speed, 14 years of a nuclear plant for one tiny robot, 42 years one way at 10% of light speed, 10,000 years to a star that, by galactic standards, is barely down the road, The arithmetic is the truth. The dome is the lie. The lie is not malicious. The dome was not built to deceive you. It is simply the way the human visual system processes incoming photons. The truth required 2,500 years of careful astronomy to extract, and it still has to be reminded into mind each time the eye looks up, because the eye keeps insisting on its own interpretation. That is fine. The dome is beautiful. The painted ceiling impression of a celestial sphere has been one of the great steady comforts of human existence. The same dome under which every shepherd and sailor and traveller has slept for as long as there have been humans. Knowing the truth behind the dome does not make the dome less beautiful. It makes it more precise. The painted ceiling is still painted in the same colours. The same constellations still trace the same patterns. The same brightness gradients still mark the brightest stars. Only the depth has been corrected. Take one more pass at the night sky tonight, if the weather is clear. Look at two stars that appear almost touching and remind yourself gently that they are not. They are perhaps 50 light years apart. Their light has travelled to your eye along separate paths, from separate worlds, and arrived at the same instant by the geometric coincidence of your point of view. Notice the way your eye still wants to read them as neighbours. The visual cortex is doing the same thing it has always done. The dome is still painted, the constellations are still constellations. The only thing that has changed is what you know about what is behind them. The depth is corrected. The distances have moved from a few feet to trillions of miles. The stars are no longer points on a ceiling. They are flames in a cathedral. The universe is not malevolent. It is not refusing to introduce us to anyone. It is simply built to a scale at which the question of introduction does not, on its terms, arise. The candle flames burn in the cathedral. Brief, beautiful, scattered across an immensity that dwarfs them all. Each one illuminates its own small circle. Each one casts no light beyond it. The darkness between them is not empty in the way an empty room is empty. It is the medium of the cathedral. It is what the cathedral is made of, almost entirely. The flames are the exception. The dark is the rule. The candle flames burn for a while, and then they go out, and the cathedral continues, dark and patient and unchanged. Stand still for a moment with the image. Some of the flames you see are far enough away that the light from them is old. The flame itself, in the room with you right now, may already have burned out. What you are seeing is the memory of its light, still travelling, still arriving, still warm to your eye. There are flames that lit and extinguished long before you were born, and their light is still in transit through the cathedral toward where you are standing, and it will arrive eventually, and you will see a small bright circle, and you will know, intellectually, that the candle that cast that circle is gone. There are also flames that have not yet been lit. Somewhere in the cathedral, candles are waiting to be lit by hands that have not yet come. You will not see those flames. You will never see them. They will be lit long after your own flame has gone out, and the cathedral will receive them quietly, and the dark between them will be the same dark it has always been. This is the picture the physics of the previous 12 parts has been building toward. It is not a sad picture. It is a description. The cathedral is what the universe is. The flames are what minds are. The dark between is what reality is built out of. We are not separated from each other by mistake or by malice. We are separated by the geometry of the place. The cathedral was built before any of us were born, and the cathedral will continue after all of us are gone, and the cathedral has always been a place where the flames are small and the dark is wide. Walk back toward your own candle. You can find it by the small circle of light it casts, the only circle you have ever really been inside. Stand beside it. The flame is warm. The wax is real. The light is real. The world it shows you is real. The other flames, the ones in the middle distance, the ones whose old light you can see drifting toward you across the cathedral, are also real. They are also warm in their own circles. They are also illuminating real worlds. You will never reach them. They will never reach you. But you can see from where you stand that they are there. That is what the cathedral offers. Not contact, not company, just the knowledge that the cathedral is not empty. That you are not alone in any cosmic sense, only in the practical sense that the room is too large and the flames are too brief, and the dark between is what the room is mostly made of. Settle into that for a moment. The universe does not prevent life from arising. It prevents life from meeting. Those two statements sound similar, and they are very different. A universe that prevented life from arising would be a universe in which the conditions for life never existed in the first place. A universe that prevents life from meeting is a universe in which the conditions for life exist abundantly, and the conditions for contact between those instances of life exist not at all. We live in the second kind of universe. The conditions for life are so common that 6 billion Earth-like planets exist in our galaxy alone. The conditions for any of those planets to send a representative to any of the others, or even to learn that any of the others exist, are essentially nil. It is a strange asymmetry. The universe is generous with the ingredients and miserly with the introductions. Somewhere in this galaxy, an intelligent civilization may be staring at the sky tonight, wondering if anyone else is out there. They may have cities, they may have technology, they may have starships of their own design, slow ones, the only kind physics permits. They may have done their own arithmetic. They may have arrived at the same conclusion we have. They may have decided, as we may eventually decide, that the universe they live in is the kind of universe that wants them to look up and wonder, and does not want them to leave the room they were born in. That is not loneliness in any easy sense. It is the shape of the place. It is how the cathedral was built. The walls are very tall. The dark between the flames is very wide. The flames are warm where they burn. That is what we have. It is more than nothing, and it is, in its quiet way, a complete description of the situation we are in. The universe is a cathedral. The dark is the medium. The flames are the exception. The cathedral does not need our permission to be what it is. The cathedral does not need our understanding to continue. The cathedral was here before we lit our flame, and the cathedral will be here long after our flame goes out. And the same is true for every other flame the cathedral happens to be holding right now, scattered across its enormous quiet floor. It is, in fact, an extraordinary amount when you consider what the universe could have given us instead. The universe could have given us no flames at all. It could have given us no candles, no cathedral, no observers to notice that the dark between the flames is wide. Instead, it gave us one small flame, our own, and a vantage point from which to see, with patience and careful arithmetic, the outlines of the cathedral around us and the faint distant suggestion of other flames we will never reach. The barrier is not technology. The barrier is reality. The night sky still looks like a neighborhood. After tonight, you will know what is actually behind the dome.